Okay, so welcome back. Let's try to fill in this table according to the algorithm as well as the notation we showed before. And we will start from the first row first. We will start by the RS subquery first. So given two relation R and S, we want to calculate the join between R and S. And we also want to calculate the size, the cost, as well as the plan for this subquery. I hope you still remember, right? We define the size for the subquery RS equals to what? Equals to 0.01 times the size of R times the size of S, right? According to the previous pages, we know the size of R will be equals to 2K, right? And this S will be 5K, right? So the size for RS will be equals to 100K, because here we have to calculate 0.01 times 2K times 5K, which will be resulting in the 100K as the size for RS. Also, according to the cost matrix, right, we know this cost for the RS will be equal to 0, because for the scanning, the cost will be 0, right? Also, both R and S, they are both individual relations, and we will not consider any cost for them. As for plan, because here we only have two relations, their plan will be just R joins S directly, right? As to the RT, it will be similar. We will need to calculate the size, the cost, as well as the plan. So for the cost, for all the combination of pairs of relation, their cost will all be zeros. As to the plan, because we only have two relations, their plan will just equal to the R joins T, R joins U, S joins T, and T joins U, right? So they will be the same as the subquery here. In the main focus will be the size for this kind of subqueries, among any pair of these relations. For RT, the size will be equals to 0.01 times 2K and further times 3K, right? It will be resulting in 60K as the size for RT. And then RU will be 20K and ST will be equal to 150K, SU will be equal to 50K, and TU will be equal to 30K, right? Then the size for the subqueries. And the cost for all of them, they are 0, and the plan will be equal to the subqueries because we only have two relations. Okay, so these are the pairs of the relation for composing the subqueries. Next, we will go to the subquery involving three relations instead. We will take the first one as an example, like a joins between R, S, T, right? So, first of all, we have to calculate the size for RST, right? Because according to the equation we showed before, the RST size will be equal to 0.01 times R size is about 2K, right? S size is about 5K, and T size is about 3K. So therefore, the result will be about 3M for the overall for the subquery, right? And the interesting part here will be for the cost of this subquery. According to the previous page, we have to enumerate all the potential combinations of these relations, right? So for this RST, it can be decomposed into what? Into RS joins T, RT joins S, and ST joins R, right? We have three different combination options. So for this RST, we have different combinations, right? It can be composed by RS joins T, ST joins R, and RT joins S. We have three different combinations, right? Also, among them, the minimal cost will be equal to actually 60K. And we can achieve this 60K by joins RT first and then further joins S. And how to get this 60K? Because according to this plan, we have to calculate RT first. And when we further join the result with S, so the cost will be equal to what? Equal to the cost of RT plus the cost of S plus the size of RT, right? Because we know the cost of RT and where the cost of S will all be equal to zeros. Then the cost finally will be equal to the size of RT. According to the previous pages, the size of RT equals to 60K. Therefore, the cost for RTS will be equals to 60K here, right? And you're going to try to calculate the cost for different combination of this RST. This 60K will be the minimum cost actually. In a similar way, we can also calculate the cost for RSU, RTU, and STU as well for both the size, the cost, as well as the plans. You can try this by yourself on your papers. Okay, so this is the result for the joins among three relations. Then we can go to the final result for joins among four relations. So the size will be very easy to calculate, right? Because we have to calculate the size to be equal to 0.01 times R size will be 2k, S size will be 5k, T size will be 3k, and U size will be 1k, right? The final result for the size will be about 30M, right? As to the cost, we have to enumerate all the penta combinations for this RSTU, right? It can be decomposed into what? Into either a combination of three relations joins one relation, right? RST joins U, STU joins R, and other options. Or we can decompose them into two pairs of relations, like RS joins TU, or RT joins SU, RU joins ST, etc. So according to our formula we showed before, we can calculate these different combinations as well as the cost. So we can find the optimal combination will be equals to RT joins SU, and the cost introduced by this combination will be equal to 60k plus 50k, because this cost will be equal to the cost of RT plus the cost of SU plus the size of RT plus the size of SU, right? The cost of RT and the cost of SU will be all equal to 0, and the size of RT equals to 60k, and the size of SU equals to 50k. So therefore, the cost for the RSTU according to this plan will be equal to 110k as a result. So you can see, according to this table, we can find the optimal plans for all the potential subqueries among this RSTU, these relations. And we can get the final optimal result for joins of this RSTU together. It will be according to the plan of RT joins SU. The final cost will be equal to 110k. Okay, so this is the example. Okay, we want to show you how this dynamic programming-based algorithm works. And you can also try to practice this example by yourself on your papers, so you can understand how this algorithm works actually. Okay, so this is the example, and we will move to the next page for summarization of this algorithm and also introduce how to estimate the size of the subqueries.